We're going to be testing circuit breakers in this video. I have two circuit breakers here in front of me. This is a 2-pole circuit breaker, and this is a 1-pole circuit breaker. We're only going to be testing the 1-pole circuit breaker, but I do want to explain what the difference between these two types of circuit breakers is. In the 2-pole circuit breaker, we have two switches that are bonded together here, so that if one side of the breaker trips, then the other side is going to trip too. A 2-pole circuit breaker is often used as a main switch. For example, in a house, you would have electricity coming into this circuit breaker and then branch off into other 1-pole circuit breakers, which would then feed circuits throughout the house. Now, the reason it has two switches rather than just one at the main switch is because this circuit breaker is capable of switching off the neutral side and the hot side simultaneously if there's a problem. A 1-pole circuit breaker like this one would always be installed on the hot side of the circuit rather than the neutral side. If you have a problem in your circuit, then you want to make sure that the hot side is switched rather than the neutral side. So the hot side of the circuit would usually feed up through the bottom of the circuit breaker, and then the hot switched side would feed up from the top side of the circuit breaker. These circuit breakers here are white color. I find that that's very common in Europe and in Asia. In North America, circuit breakers tend to be colored black. I don't know the reason for that, but that's the way it is. Circuit breakers care more about current than they do about voltage, but they do have a rated voltage. These circuit breakers right here are rated for 230 volts or 400 volts. 400 is referring, I suppose, to three-phase, and the 230 is referring to a single phase, but it's just a 1-pole breaker. And again, the current is what really matters here going through the breaker. On the front part of this circuit breaker here, it's labeled B 1 ampere. B refers to the trip curve, and I'll say something more about that in a moment. And 1 ampere refers to the maximum allowable current that you can pass through the circuit breaker without it tripping. If I flow exactly 1 ampere, or say 1.1 amperes of current through this breaker, that doesn't mean it's going to trip instantly. The amount of time it takes a circuit breaker to trip depends on how much more than the rated current you try to send through the circuit breaker. If I try to, for example, send 5 amperes or 10 amps through this circuit breaker, it has a solenoid inside of it that will immediately pull the contacts apart. It will trip nearly instantaneously. But if I have just a little bit more current than the rated current, say 1.5 amperes or 2 amperes, the circuit breaker might allow that current to pass for several minutes before it trips because it has a thermal tripping mechanism for those lower currents. Let's take a look at tripping curves for various breakers. The type of circuit breaker that I'm holding in my hand here has a type B curve, and this is very common for residential installations. Type B circuit breakers will trip rather quickly when you have 3 to 5 times the rated current going through it. Now, there are circuit breakers that can trip faster. For example, a type Z circuit breaker will trip faster. Type C, D, K, and D circuit breakers, however, will trip more slowly, and you'll find these slower tripping circuit breakers used, for example, in some industrial situations where a motor might require quite a lot of starting current. You don't want nuisance tripping, so you could use, for example, a type C circuit breaker in such a situation. As I mentioned, circuit breakers have thermal trigger and magnetic trigger. The magnetic trigger involves a solenoid down inside the circuit breaker, which will pull the contacts apart very quickly. That's to protect against short circuits, for example. The thermal trigger happens a little bit more slowly. What we're going to do here in the demonstration is to measure the trip curve for this 1-pole circuit breaker right here. We'll put the 2-pole circuit breaker aside since I'm not going to be measuring that one. This circuit breaker is only rated 1 ampere. That's a rather low rating compared to what you would normally find in a breaker box, for example, in a house. We're not going to be testing this circuit breaker at 230 volts. We're going to instead test it at a rather low voltage, and we're going to use the DC power supply. The tripping curve for DC currents will be a little bit different than the tripping curve for AC currents, but what we care about here is to just get the general shape of the curve. The circuit breaker, again, doesn't care so much about the voltage across the circuit breaker. It cares more about the current going through it. When circuit breakers are actually installed, the main purpose of the circuit breaker is to protect the wiring. It's to guard against fires. It's not to guard against shocks. So the wires that feed into and out of a circuit breaker have to be matched in order to handle the current that the circuit breaker is rated at. The wiring that I have here in front of me can handle 1 ampere of current, so we're okay when it comes to wire gauge. I'm going to go ahead and screw some wires into the top and bottom of this circuit breaker and set up a test here. So I'm hooking the positive side of our DC power supply here to the lower part of the circuit breaker. I have 7 resistors here. Each of them is 47 ohms rated at 10 watts to serve as the load. So we have here a circuit consisting of a DC power supply, a switch, and a resistive load. V equals IR for our resistive load here. So as I change the voltage of the DC power supply, the current passing through the load and the circuit breaker will change simultaneously. We're going to start with rather high currents and see how long it takes the circuit breaker to trip, and then work our way down to lower currents. We're going to make a graph of the time it takes this circuit breaker to trip as a function of the current that I'm passing through the circuit breaker. Let's try 2.75 amperes now. Let's try 2.5 amperes now. Next, we're going to try 2.25 amperes. By the way, in between each of these measurements, we've also put in some time to allow the circuit breaker to cool down. Let's try 2 amperes now. We're mostly in the thermal tripping region at this point. This power supply can't really give us the high currents that we need in order to get into the magnetic tripping region, so our curve is mostly going to be in the thermal region here. Let's try 1.75 amperes. It's taking a bit longer to trip now. Let's go to 1.5 amperes and see how long it takes. Well, it's already been quite a long time here, and I'm getting tired of waiting for this circuit breaker to trip. I think we have the idea here. A common misconception about circuit breakers is that they'll trip when you have more current flowing than what's printed on the circuit breaker, but obviously that's not true. It takes these things quite a long time to trip. But they do have a really ingenious design. If you short circuit, then they'll trip immediately. But if you flow just a little bit too much current through these breakers, it takes forever for them to trip. I hope that you've learned something from this video and you've enjoyed watching circuit breakers trip. We have a whole series of professionally filmed and edited videos in order to help students learn the fundamentals of electricity. If you like watching this particular video, then you might like to check out some of our others too.